I'm Michael. I'm a PhD student at the Technical University of Darmstadt, and here I'm going to present you my work on robust value iteration for continuous control tasks. Sim-to-real is one approach that lets you train the policy in simulation and then transfer it to the physical system. However, the resulting policy has to be robust to bridge the sim-to-real gap. If the policy is not robust, the policy will fail when transferred to the physical system due to the mismatch in dynamics. The standard approach to obtain robust policies is domain randomization. However, in this paper, we propose an adversarial reinforcement learning approach. In this way, we don't randomize the model parameter, but let the model parameters be controlled by an adversary. The adversary controls these parameters to minimize the reward. In this case, we do not optimize the expected reward, but the worst case reward, and therefore obtain robust policy. More concretely, in this paper, we solve the Hamilton-Jacobi-Isaacs differential equation using value iteration. Therefore, we solve the min-max problem and obtain the robust policy. The main insight of this paper is that the optimal action and optimal adversary controlling the parameters can be described in closed form if the dynamics are controlled affine and the reward is separable in a state and action cost. In this case, the optimal policy performs gradient ascent on the value function, while the adversary performs gradient descent on the value function. The gradients of the value function are then projected onto the controlled quantity, so df d or df du, and the step size of the action adversary depend on the action cost in terms of the policy. So if the action cost is high, you take small steps. If the action cost is small, you take large step. And for the adversary depends on the admissible set. And the admissible set is necessary because otherwise the adversary would be much too powerful and would outpower the optimal policy. In the paper, we also provide the theorems for state, action, and observation adversary. Using these analytic expressions, we can come up with an easy update for the value function to learn the optimal value function. We just need to substitute the optimal adversary and policy into the value function update of value iteration, and we have a simple update without optimization. Therefore, the resulting robust fitted value iteration approach takes as input the model, a data set, and the admissible sets, and it returns the optimal value function, which also implies the optimal policy. In the first step, we compute the n-step value target. We use the n-step value target as this increases the convergence speed. This formulation is basically identical to the forward view of the eligibility trace, but this time it's a continuous time formulation. In the second step, we fit the value function to it. So we optimize the network to fit the targets. Iterating these two steps will lead to the optimal value function. The current algorithm is offline. However, we can also do it online by just adding the samples of the current policy to the dataset and then using the updated dataset to compute the targets. Within the experiments, we applied it to the standard control task, the Furuta Pendulum, and the cartpole. We also varied the masses for the pendulum to test the robustness. So here you can see the Furuta pendulum with varied masses from minus 21% to plus 21%. For all these systems, the resulting robust policy obtains a successful swing up and balancing. Therefore, the obtained policies using robust fitted value iterations are robust. However, we can also observe a shortcoming of the worst case approximation because the policy does everything very forcefully, and this leads to shattering when balancing the system. The shattering is basically caused by small delays in the control loop. Also, we compare the obtained cost to the standard approaches of uniform domain randomization, and we can show that the optimal policies is more robust to changes in the pendulum mass than the domain randomization approaches. However, we can also see that the action costs are usually much higher compared to domain randomization because the policy is just too conservative. To summarize, we derive the optimal adversarial policies for state, actions, and observation and model disturbances. We do this in closed form for control affine systems and separable reward. We then leverage these analytic expressions for value iteration to learn the optimal value function and the robust optimal policies. Within the experiments we showed, that the resulting policies are robust and can be transferred to the physical cartpole and the physical Furuta pendulum.